Okay, this hour we'll talk about our next algorithm. Um, and the very first algorithm we talk about is linear regression, and this hour we'll go over logistic regression. The difference between logistic regression and linear regression is that when we talk about the target y, okay, um, if y is numerical, and then we will model such kind of problem as regression problem. But if y is categorical, for example, if it's either 0 or 1, then we will model such kind of problem as a classification problem. But right here, the logistic regression, although its name is logistic regression, but it is some kind of algorithm that helps us to um, solve the classification problem. So that means the target of logistic regression is categorical. So in this example, we'll tell you how to run logistic regression and what is the mathematics and details in this hour. Okay, and we will explain why it is a classification algorithm, but its name is regression. So here is a very simple example. Let's take a look at this table. Okay. Um, in this example, as usual, we have n data point, and we have only one feature. Okay, which is score, and the corresponding target y right here is either this game. Okay, the NFL game is win or loss. So we use loss. That means loss. And some game you win, right? So that is win. And here are some scores of the game. Okay, and I think that's something like that. So the target y is win or not win, and the score is a feature of this game. Okay, of course there should be any other features can use to be describe this game, but we only use one feature, which is the score. Okay, so basically x is also numeric, right? And the y is a binary value, either 0 or win, which is 1. Okay, so basically take this one as an example. Okay, so basically if you draw the x and y right here, and you can see that because y has only two values, so it is either right here, okay, which means win, and the other part of the data is right here, it is indicate lose, right? But since the x and y can be represented as numbers, so you can use linear regression to model such kind of problem. But the final result, if you use a line to describe this such kind of a problem, this line would be very strange. Although this origin line has the smallest MSE value, okay, the MSE value is described as the square of the arrow, the sum of the square of the arrow, right? Although this orange line has a smallest MSE value, but it looks strange, right? And also, if you model y like this, okay, for example, if you input the data x right here, for example, x equals -1, and the result would be right here, right? Y might be something like minus 0.1. That means if you score -1 score, and the probability of win would be -0.1. That kind of data would be very strange, right? And there's some other data which is right here. That means if you score more than, for example, 55 points, and your winning probability will be higher than 1.0, which is not a feasible solution. So it is very strange to use the linear regression to solve such kind of problem, although the x and y are both can be represented as a numeric data. So in order to solve such kind of problem, you need to find another kind of model, try to modify the data itself. So maybe the data would looks like this. You need another shape, another line, okay, to describe when you score more and the winning probability will be higher, and you score less, the winning probability will be lower. And for data like here, sometimes if you score, for example, 26 points, but you lose. But sometimes when you score 25 and you win, right? There's a probability to describe such kind of data, right? So maybe you need some shape like this, which is called a ACE curve, okay, to describe such kind of relationship between the point you score and the probability of your win. Okay, if you take you can also draw such kind of figure. Okay, it demonstrates the probability of win when you score in this range, and the probability of your win lose when you in this range. Okay, but we need a more feasible shape, or a more feasible model to model such kind of data. Okay, such kind of data. So that is you cannot simply just use a simple linear regression to model such kind of data. Okay, so here is the result. Here, that is the model we use. Okay, but I would explain why this model is used and where it comes from. Okay, but that is the final result. That means when you enter the when you enter your x, okay, which is the score, okay, and it will output some kind of probability. Okay, the probability is a ACE shape. Okay, it means if your feature, if you have a bigger feature, and the corresponding result of your probability will be higher, and if you input a lower some lower value of your feature, and the corresponding probability will be lower. And in the middle, it really depends on your data. Okay, the data can be something. It depends on your data. The shape and the slope of this shape can be changed. Okay, it depends on your data. Okay, it can be like this one, or it can be like this one. It depends on your collected data points. The data point will help us to model which kind of line, shape, slope, okay, we will use to fit the data points. Okay, so we'll talk about later. So but that is the final result. The mathematicians tell us you can use such kind of formula to model your data. Okay, so before we continue, we'd like to introduce two concepts. Okay, it's right here. Okay, the first one is about the probability. When we talk about probability of a win, okay, it is very different. The definition is very different from odds of a win. Okay, take something for example. If you are a team manager, and usually For example, you always win 3 games out of 4, right? So that is win, and that is lose. Okay, so when we talk about probability of a win, that is very simple. That means 75%. And the mathematics we describe such kind of thing is that the probability of y equals win or lose. Okay, and 1, we define 1 as win, right? And that is 4 out of 3, right? That is 75%. And the other one is the probability of lose, which is 25%. Right, that is very straightforward. Okay, that is very straightforward. But when we what exactly this one, okay? But what exactly we would like to model in this kind of shape, okay? So that is straightforward. That is x1. That is the score. But what is the y-axis? Y-axis is not the probability of win. That should be a conditional probability, which is probability of win conditioned by your feature equals certain value. In this model, the axis of the y-axis, okay, the y-axis should be something like that. It is not probability of win. It should be a conditional probability of win under when you score certain points. Okay, so the definition is quite different. We are not calculating the probability of win. We are calculating a conditional probability of win under we score certain points. Okay, so make sure you understand that. And the second thing is we would like to talk about is odds. Okay, the definition of odds is like this. Okay, that means the ratio of success, which is 3 over the probability of not success, which is lose. So that is 3 to 1. So the probability 3. The odds of win is 3. And of course, here is another definition of odds of lose. So that would be 0.33. Okay, that is the definition of odds. So let's take a look at this figure right here. Because you either win or lose. So, for example, the P is the probability of win, right? So the 1 minus P is the probability of lose. Okay, so we have these two equations. So if we simply just plot the odds of probability in at the left hand side, you can see that when the odds value equals to 1, so that is this point. Okay, this point the probability is 0.5, and odds value right here, it should be 1. So when we use odds value to describe the winning or losing situation, okay, if the odds value equals 1, that means the probability is 0.5. That means you win or lose, the probability is the half, right? So but when you draw this figure, okay, that looks very strange, because when you lose more than win, the odds value will be smaller than 1, but it will never be lower than 0. So the range is between 1 and 0, right? But when we talk about winning, right, the range the probability, the range of probability is still between 0.5 to 1.0, right? But the range of odds would be 1 to infinity, right? So this figure looks very strange, even if it is just a very simple function of p, but the shape looks very strange. So most of the time when we when we use odds to represent winning or losing, using the odds value directly is very it's not it is very strange, right? So usually we use a log value, or we use log of odds. So it has a very specific special name called logit. So sometimes we use logit, okay, which is a long and odds value to describe different situation of winning or losing. And this figure becomes symmetric right here. So if the logit value is smaller than 0, which is right here, this part, okay, is smaller than 0 to minus infinity, okay, that means the team or the horse or the game, okay, you bid, the team is a little bit worse because it lose more than win, right? But at the right hand side, if the logit value of a team is larger than 0, that means it has more wins than lose, okay? And this figure becomes symmetric. Okay, so that is plus. So sometimes we use logit value to describe a winning or losing situation of a team or of a horse or a race car, something like that. So it is more a more feasible way to describe such kind of a situation rather than simply just use odds if you use logit to describe it. Okay, and after that, okay, so here is the probability p, right? Some probability, and that is some value that we can describe winning or losing, right? So mathematics can tell us that you can simply just flip this figure, okay? So we exchange the x value and y value. So we put p right here, and we put the logit value right here. And the shape of this figure would be very nice, which means the probability will be still between 0 and 1, and logit value will be something like this. And as you can see that this figure is very similar to what we would like to model in our previous problem, right? Left hand side is probability of something, and the x-axis is some value. Okay, so the mathematics can tell us that if we know, so that is so the mathematics can tell us that if we can model our problem by using certain function, for example, g function, and that g function has a parameter which is exactly our x value, then we can map the x value, which is score, in our problem, and we can map this score by using a g function to use it to simulate the logit p value. So it's kind of mapping, okay? And then we can use the logit function, which is right here, to calculate this corresponding probability, which is what we want to output, right? So that is the basic idea of logistic regression. But the problem is that what is the G function right here? How can we map our score, which is our feature, to an other value, and that value can help us to calculate the corresponding probability. Okay, so let's just simply put the G function right here. We first tell you how do we use the logit value to produce the probability. So here, because the shape of the upper right figure is that it's right here, right? That is P equals long. Sorry. Logit P equals long P over 1 minus P, right? That is the result, right? So when we flip the value, so here's the calculation. How do we flip this result? Okay, flip this figure. So you can take a look at by yourself. So after we flip the value, it would becomes the probability equals 1 E okay, we simply just flip this value and it becomes this one. Okay, so we simply just do that. Okay, so the shape is exactly what we talked about. The function is a value equals to 1 over 1 plus E. Okay, and the power value right here is minus log value. So if we write it in this way, it should be equals to okay, the value right here is log P, right? But we define a G function right here, so this should be something like this. Although we don't know what exactly the G function is, but we know the form of this kind of model should be looks like this. Okay, so again, P is exactly the value we like to use. So our model looks like this. I can find a function G which can help us to map the feature, which is X, to another domain which is called logit P. And we use the logit P and this equation, and then we can generate the corresponding output of the P, which is exactly the y hat value we like to calculate. So that is the basic idea of logistic regression. So the next problem is, how do we find such kind of G? Unfortunately, the mathematicians tell us that it's right here. Okay, there are some other notation we used right here. For example, right here, the G function. Sorry. Sometimes I use Z right here to replace the logit value because logit P. I use the Z because it's much simpler to represent such kind of concept. Okay, and right here we say that the mathematician tell us that we can assume that the Z, which is the logit P value, which is the G function, or what is the logit P value. We assume this value, okay, is linear to your feature. So in right here, so it continues right here. We assume the value right here is linear to X, which is your feature, and it is assumption. So we basically we don't know if it is correct or not, but we simply just assume it is. So it could be something like this, linear, linear to x1. Although we don't know if it is true or not, but we assume it is linear, so we can write it in this form. So your model becomes this. It is some kind of assumption, just like what we have learned in linear regression. Although we have the x value and y value, but we don't know if it really linear or not, but we simply just assume it is linear between the x and y in linear regression. So in logistic regression, it's the same. We don't know the relationship between z value or between z value and x value, which is the log value, but we simply just assume it is linear. So the formula becomes that. Okay, so here's the result. And if you have multiple features in your data set, you can simply write this form as we mentioned before, it is just extend your formula from one single variable to multiple variables. Okay, so that is how we model such kind of data. So after that, we can see that the model becomes this one. Becomes this one for a single variable model. Okay, and as we can see that if you have different slope and intercept, which is the A and B, and your shape looks different. So it's really depend on the data you collect, the data you collect right here, and how they act with each other. So you will have different types of different shapes of this shape, and this shape has a name. It is either called sigmoid, MOID, or called sigma, or log P, something like that. This shape has several different names, but they all indicate the same function, which is this one. Okay, so so from now we use this function to describe the data we have here. If your data is the target value is binary and it's either 1 or or 0, and you believe your data is if you have a larger x and you have a higher probability of y, and you have a smaller x feature and you have smaller probability. So if you want to model such kind of data, logistic regression will be nice for you to describe such kind of data. Okay, so so here we again the probability we mentioned right here is something is like this. It's a conditional probability. Okay, so in order to find the best curve, the best A and the best B in logistic regression, there's something I'd like to show you, some data I'd like to show you. Okay, so if you have a data, if you have some data and we assume we have only one feature, okay, so that is y, that is maybe that is 4, 5, 11, 24, 25, 26, 44, 46. If you have a data like this, okay, its corresponding y is 0, 0. I mean, you know, sometimes the data is not that smooth, so sometimes you win when you win even if you have a lower score, and sometimes you lose even if you have a higher score sometimes. Okay, so in order to find the best fit feature, of course, again I said Of course, you can use linear regression and you can use MSE to calculate the best line. But in logistic regression, we need to find the best S-curved line. So the evaluation function of logistic regression is a little bit different from MSE. Okay, again, right here, the MSE is defined as, okay, we have n data points, so we go over all the data point, right? And we have the real target, okay? And we calculate the error of your model, and we put a square right here. So that is MSE, right? But in logistic regression, we don't use MSE. We use another concept, okay? The concept is very similar to MSE, but it's different. The evaluation function is like this. Again, we should go over the entire data, okay? But you have to take a look at this value, because the shape we define right here is a S shape. It is a continuous shape. So basically, it cannot output 1 or 0 directly. Usually, okay, we set the threshold at 0.5. So if the probability is larger than 0.5, and we output 1. If the probability is smaller than 0.5, and we output 0. So we have a threshold right here. So basically, when you use logistic regression to calculate the y-hat value, it should be something like this. Because those value is lower than 0.5, so we output the value as 0. And so on and so forth. So if the value is very large, for example, and the output value should be 1, so right here, if the input x is 24 and the value could be and the corresponding output value should be 0, 1, and 1 right here. And as we can see that it's right here. This value and this value is not the same. That means this model, okay, we call it model 1, okay. This model 1 has some error because the prediction is the y-hat value is 0.49, and our value should be 0, but actually the actual y is 1, so that is an error. And this is an error, right? So 2 errors. Maybe we have 2 errors in this data set. So in order to evaluate the performance of different model, and of course there could be some other model, which is model 2 right here, and it has certain different 0 and 1 result right here. So mathematicians tell us that we can use some other kind of evaluation method to help us to deal with such kind of things. Okay, you have to think about this. Okay, because it is less than 0.5, so the result is 0. But from the perspective of management or decision making, okay, if a model tells you, okay, that is 0, that means if you score 25 points and you may lose. Okay, so that is lose. You may lose the game. But you know the probability is very, very close to 0.5. The situation is very different from if you score 4 points and the model tells you the output value is 0. That means you lose, definitely lose. But here is the probability of this score, which is 0.001, which is much less than 0.5. So although this model M1 can output 0 and 1, but there is different for data point like 4 and 24 because the probability right here is a little bit different. So most of the time, you don't want your model to output a y-hat value which is close to 0.5. That means the model can barely output 1 or 0. But this model can precisely output 0 or 1 when the y-hat value is very small or very large, close to 1 or close to 0. So most of the time, you don't want to get output value near 0.5, right? So we need some more aggressive way to evaluate the result of logistic regression model. So here it is. So basically, okay, let's take a look at blue. Okay, if the value is very close to 1, and you simply just put this value right here. If it is right here, okay. So you do this, okay. If this is very close to 0, and you just use 1 to minus 0.001, so this value should be 9991 9. Okay, if its y value is 0, you simply just use 1 to minus this value. So that will be 0999. That would be 0985, and so on and so forth. Okay. So for this one, that would be 55, 0.55, right? Okay. So, and I would like to show you this one. The actual value is 1, right? So you simply just put this value right here. And that is 0, that you use 1 to minus this. Okay, so the other way to evaluate how good this model one is, you simply just multiplex all these blue values. So that is, you simply just multiplex all these values. Okay, so if y equals 1 and the value is your y hat, if the actual y value equals to 0 and you use this value, you simply just so the result is this one. You simply just multiplex all its values, and as you can see, if this value is very large, which means very close to 1, and that means this model is very good. This value is very close to 0, that means your model is worse than all the others. So for such kind of evaluation, it makes the value right here near 0.5 to push to some value which is near 0.0, and we'll push this value to 1.0, because you just use such kind of evaluation equation to evaluate different models. So if a model it has less green part, right? That means every value will be close, every y hat value will be close to 0 or close to 1, and that model would be better. We want to eliminate the value near to 0.5. Okay, so that is the evaluation function we use, which is a little bit different from MSE, but it's very the concept is quite similar. We still go over all the entire data set. So we have n, we have from from 1 to n, right? But we don't calculate the error. We use y hat and y corresponding to its y value. So we multiplex all these values. So if it's close to 1, then the model is good. So this value is called likelihood estimation. And we like to maxima. So that is L. We like to maxima this value. The better the model is, the higher the higher likelihood it has. So that is how we evaluate different models in logistic regression. So right here. So again, so let's take a look. How do we do the rest of the calculation to find the best model? Okay. So again, that is the probability we want to have. We want to calculate. So that is y hat. Right. So that is p. Okay. So it's 1 minus y hat, or 1 minus p. Okay. But mathematics can tell us that you use two different because condition probability is a little bit difficult to manipulate. So we transform these two condition probability into one single formula. So let's take a look at this one. Okay, take a look at the red one. Okay, if y equals to 1, and the value should be a function of x. Okay, and theta is the parameter. So take a look at this one. If y equals 1, then y equals 1, right? And y equals 1. So 1 minus 1, so that is 0, right? Anything, okay, powered by 0, that means 1. So that is, it is the same, right? So again, take a look at this, the next one. The green one. Okay, if y equals to 0, 0, okay, so y equals to 0, 1 minus 0, everything, okay, powered by 0, so that is 1, and that is 1, so that is, the result will be this one. Okay, the same as this one. So that is just some mathematic tricks. Okay, so we can combine these two equation to one single equation. That is just a trick. That's nothing. It's just a trick. Okay, so that is that is y hat, right? But we use one single formula to formulate y hat. Okay, so the next thing is that we like to calculate the likelihood value, which we times every y hat. So that is y hat, right? We times every y hat among all these n data. So that is the evaluation function we like to calculate. Okay, and that is likelihood, right? And we want to maximize the likelihood value. Okay, so here we have a formula like here. If we have the maximum value of this likelihood function, and the corresponding theta will be the theta star, which is the optimized value of your parameter. This parameter can have the maximum likelihood value. And again, right here. The f theta xi in logistic regression, it is one over 1 plus e and powered by this value. Maximum likelihood can be used in other algorithm, but right here in this hour, this function is linear logistic regression, so we use this as the f function right here. Okay, so we simply just try to calculate the maximum value of likelihood. But for mathematicians, it is not that trivial to find maximum value. So again, there are some mathematic tricks, okay? In order to find the maximum value of this likelihood, we can simply just calculate the minimum value of the minus likelihood. It is the same. To find the maximum likelihood is exactly the same as find the minimum minus likelihood. Okay? And again, right here you can see that there is a log right here. And that means because the likelihood has so many multiplex right here, right? So because log is an increment function, right? Log is increment function. So if the value right here is large and its log value is still large, if this value is smaller and this log value is smaller, because it is a incremental function. Okay, so if we would like to find the maximum likelihood, we can use some mathematic tricks to find the minimum value of minus log likelihood. The result will be the same. Okay, the result will be the same. But with these mathematic tricks, it is easier for us to find the value. Okay, so again right here. Okay, we'd like to find so first we put a minus right here, so the minus is right here, and then we put the log function right here. Okay, so make sure you understand that when we talk about log on a function, okay, especially a polynomial or function, okay, we put a log right here. So for this purple part, the yi, which is the power right here, should be put right in front of here, and the f function here still be here, but we have a log. Okay, and for the times right here, it becomes plus if you apply log function on it, right? So here we have the power value, so it should be right here, and the 1 minus function should be right here, but we have a log here, right here. Because it is time, right? So it becomes sigma right here. So if you applied minus log to maximum likelihood function, the result would be look like this, because it has a lot of different addition right here, right? Addition, and it is the sigma. It will be easier for us to find the minimum value with this form. So after that, the result will be like this. and so on and so forth, so on and so forth, so on and so forth. The result is like this. In order to find the maximum likelihood, okay, you have to find the minimum value of this function, if you can do so. Okay? So, so again, let me see. And again, you can use any other mathematical tools to find the minimum value of this when you, because we have n data point, right? We have O, xi, and yi in this table. So you just simply put all these data points in this formula, and it will become something very complex. But it is you can still find the minimum value of this value. And again, we don't want to directly use many complex mathematical tools to find the minimum value. So we still use right here. We skip this part, okay? We skip this part because this is how do we explain this likelihood by using some statistical way. Okay, we skip this part. But in order to find the minimum value of this equation, okay, we can simply just apply gradient descent again, because it is still some shape in a multi-dimension space, right? And it had this shape, okay, this green shape has minimum value. So we can still find, we can still use gradient descent. So we have x1 to xm, and that is the green function we have, which is the minus log long likelihood. We can still draw the figure like this, and can we still apply partial differentiation in different features x1 to xm, and use gradient descent to find the smallest least value. So again, we can do partial differentiation, so and so on and so forth, so on and so forth, and the result will be like this. That is the partial differentiation result of minus long likelihood value. So again, very similar to linear regression. If you would like to find a parameter which is t equals to 0, okay, for example, you want to find as we mentioned before, the value is the logistic regression function is like this, right? It's like this, and it's very similar. Like we like to find the minimum minus long likelihood, right? So it's very similar to we like to find linear regression, and we use MSE, which is find the maximum MSE, right? It's the same. It's the green part. The logistic regression is very similar to the purple part, which is linear regression. It's the same. Okay, so in order to find the minimum value of the MSE or the minus long likelihood, okay, we still use gradient descent. So for example, if you would like to find the A star, okay, you can start from this form, okay. So that is the first time you find the partial differentiation of this value, okay. So that is the direction of your tangent line in this space, right? And you walk to the next A surface. Oh, sorry. The result right here should be A and B. Okay, because it is evaluation function. Okay, so that is A and B, not X and Y. Okay, so you simply just select theta t equals 0. Okay, we have A 0 and B 0, and we don't know what the shape of this minus long likelihood, but it has a minimum value. So we simply just using gradient descent to find the minimum value of minus long likelihood. So that is how we do. So it's very similar to linear regression. So that's it. That is how we trying to use a S value to model the X and Y, which when Y is binary value. Okay, so that is how we use maximal likelihood to use it as another evaluation function to evaluate different models, and the best model has the maximal likelihood value, and that is how we use some mathematical tricks to help you to find the optimized parameter, which has the smallest minus long likelihood. So that is so, but as I mentioned before, that is just some mathematical details. When we analyze such kind of data, for example, that is the data, right? When we analyze such kind of data, we simply just apply some Python packages. Okay, we have sklearn, and it has a logistic regression library. We simply just feed the big X and big Y to the model, and here is the result. So for this example, the Y equals to 1, 0.64 times score, right? Plus minus 15, something like that. So every time you have a new score right here, you can simply just plug it into this function, and the probability of that game, winning that game will be the y hat value. So you can simply just put a bunch of data, and it will tell you the probability of lose and the probability of win. Okay, so again, and after that we can draw this shape. That will be the optimized shape to describe the data, the blue points. Okay, and as I mentioned, because here we have some data point which is interlinked with each other, so the shape will appropriately model those data points. Okay, depend on those data points. So and there is an interesting question, is that after we have such kind of things, what is the value of probability of a win is 0.5. So let's take a look at this one. If the y value is 0.5, that means the red value should be equals to 1, right? So that's 1 over 2, right? But how do we calculate that? And the result should be the ax plus b equals to 0, because everything powered by 0, that the result is 1, right? So that means if the score is minus a over b, and the winning probability would be 0.5 at this point. Okay, so that is just calculate the value. Okay, and again, I would like to mention this one. So as you can see that if it is a line, right? Ax1 plus b equals to 0. So that means that's the reason why we call it is logistic regression, although it is a classification algorithm, because this line is a regression line. But it is but the shape but it, the entire equation is it is not linear, but this part is linear regression. So the algorithm is still called logistic regression because this part is the regression. Okay, so again, so we can calculate value. So again, I use the iris value, okay, right here, and you can see that that is some feature, right? And that is y equals probability of y equals to certain class, okay, unconditioned by, okay, I can move it to here, conditioned by x equals x1 x2, right? So given a flower, for example some flower right here, okay, this point P, it has x1 x2, okay, its petal width and the petal length is right here. So again, simply just put it in this right here, and it tells you how possible the flower falls into this class. And of course, this equation should be something like ax1 plus bx2 plus c, something like that. And of course, the packages, or you can calculate the mathematics by yourself. We will give you the A star, B star, and C star, so that this model has largest maxima likelihood value among all these data points. I think the iris data set has 150 data points. Okay. Or sometimes you can draw this figure in this way. Okay. Again, that is x1, that is x2. In order, the green dot is y equals 0, and the blue dot is y equals 1. Okay, that means it falls into Virginica category, and the green triangle ones, that is not Virginica category. And as I mentioned, we can draw a boundary line. So let's take a look at this 3D figure. There should be some boundary line near here. And because it's a 3D, so this boundary line is not a line, it is a surface. Okay, the surface means if your data point is above the surface, that means your y hat equals to 1. The prediction value is 1. If your value, okay, if your value is right here, and the corresponding probability is lower than that surface, which is 0.5, and then your y hat will be 0. You'll be classified into 0 classes. Okay, so again, sometimes we think about what about we simply just draw the line. In 3D we simply just draw the surface. So in 2D we simply just draw this line, and this line is exactly the ax1 plus bx2 plus c equals to 0. If it is larger than 1, for example, this data point is x1 and it's y x2. If you put this value in this ax1 plus bx2 plus c, it is larger than 1. That means it's classified into y equals to 1. If it's less than 0, that means your class is 0. So sometimes we simply just draw this line, which is good enough because this boundary line specify which class is 1 and which data point is belongs to 0. Okay. So and again, sometimes you draw this figure. We have x1 and x2, right? And this point right here, they are data point. Okay, we have a lot of flowers right here, and the color of each data point and its background is corresponding the y-hat value of your model. So as we can see that here is a boundary line, which is the white line right here. So this white line, okay, all the data points on this white line, those y-hat value equals 0.5. So on the right hand side, this is the red color, and their y-hat value is larger than 0.5, so they will be classified into one class, and blue one will be classified into another class. And as you can see, that is right here. Here's the class 1, is class 0. The blue one will be classified into class 0. And as you can see that for different data points you input to this model, there should be a corresponding y-hat value, right? So sometimes when you use logistic regression to do classification problems, okay, you should not only output its class value equals to 1 or equals to 0. You should output its corresponding y-hat value, which means the probability. Because for some data points, for example right here, the y-hat value is extremely high, which is very, very close to 0. So you have a very good confidence that those data points should be classified into class 0. And of course, there are some class right here can be classified into class 1. But there's some values near 0.5. So when you make decision, be sure you output the corresponding y-hat value, so that it gives you some confidence that this value is very close to the boundary line or is far away from the boundary line. Right? Okay. So in this class slide, okay, I would like to share another data set with you, which is KDD Cup 99. Okay, it is a data set which is very popular, and it has very okay, here is it. Okay, it has many data points, okay, and that is its index. It has 41 columns, so supposedly it should be 40 plus 1, because 40 of them will be features and 1 of them will be the target. And the target is very, very simple. It is a binary classification problem. That means this network connection, okay, it has 40 different features, and you have to use these 40 features to design a classifier. Okay, if it is either an attack or a benign connection. And as you can see, there are several different types. But because in this class we only in this hour we only teach you how to use linear regression and logistic regression. So I select some columns, which is okay. Here is a y, so it is either 0 or 1. Okay, we have many thousands of data points, which is classified into 0 class, and some of them are classified into 1 class. Okay, and as you can see that I help you to select a feature. Okay, we use this feature as x1, okay, and that is y. Okay, so here I demonstrate how to use logistic regression and apply it into the feature I identify, and here's the y value. So you can see that that is the x1, that is the y, and that is a data point from that KDD Cup 99. And as we can see that, okay, there are some data right here and some data right here, and those data, okay, is attack, and those data are benign, so that is marked as 0. And we can use logistic regression to analyze such kind of data, okay, because it gives us the best S shape to model the relationship between x and y is categorical data. Okay, and again, I selected one more feature for you, so take a look at the code by yourself. Okay, so again, that's you can use the package to calculate the coefficient right here, and we can plot it into a 2D surface. Okay, that's x1, that's x2, and here is the probability of an attack. So you can see that those data points, they are very the y hat value will be very close to 0, so we can identify them as non-attack, and those value right here, they are bigger than 0.5, so we classify them into attack category. And of course, there are some data point will be near the boundary line. Okay, so that is the linear regression that we talk about. As I mentioned, you have to remember, you have to make sure you understand the underlying concept of this algorithm and how they model their data, and how do they evaluate a different linear regression model. But when we analyze data, we simply just use the packages to calculate all these coefficients and draw some figures to take a look at the data and the result of the models. Okay, so let's stop right here.